going. Okay. Hey guys, happy Friday. I'm going to take a couple minutes and work out one practice problem for you on the board here at my house in case the calorimetry problems are a little bit confusing. So I'm not going to do a lot of lecture. I'm assuming you've read the book, but I want to talk about the equation real quick. The equation that we're using for all of these changes in heat energy is the equation Q equals mc delta T. Okay, there's a spreadsheet I sent you, or rather a document I sent you that has this exact table on it. We're going to work through problem number 10, and I'm going to fill out the box just like I expect you to do for class on Tuesday. So I'm going to go ahead and read the problem to you real quick. A 345.1 gram sample of copper at 100 degrees Celsius is dropped into a 4.5 gram calorimeter made of an unknown substance. If the calorimeter has 150 grams of water in it, and the temperature changed from 24.2 degrees Celsius to 25.1 degrees Celsius, what is the specific heat of the calorimeter? Okay, so that's our problem. We're going to go ahead and solve it. So we're going to say right off the bat, what variable are we looking to solve for? What they asked us was, what is the specific heat of, the calorimeter? So we are looking to solve for this variable right here. This table gives us all the variables in the equation. This is Q, right? Q equals mass times C times delta T. And we have our initial temperature and our final temperature all as part of the problem. So I'm going to go ahead and fill this in. The first thing I'm going to write down is the information that was given to me in the problem. And what I was told is that we have a 4.5 gram calorimeter, that's how much it weighs, that we have 150 grams of water, that we have an initial temperature of 24.2 of the liquid, and then the temperature changes to 25.1. We also know that the object that was dropped into the calorimeter was at 100 degrees Celsius when it started. So its initial temperature is 100.0. Okay, and the other thing we were told is that the object weighs 345.1 grams. Now, there are a couple other boxes that I can fill in without doing any kinds of calculation, okay? I'm going to show you those right now. First of all, the calorimeter is holding the water. So if the water is at 24.2 degrees, that would mean that the calorimeter must also be 24.2 degrees. We also know that a calorimetry experiment ends when everything is the same temperature. So if the water changes to 25.1 degrees Celsius, that means that the calorimeter that's holding the water must also be 25.1, and it means that the object itself must be 25.1, because that's how we know when a calorimetry experiment is completed. The other information we should know is we should know the specific heat of water. That's one of the ones you need to memorize. It's 4.184 joules, grams, degrees Celsius. That's the units. And then finally, they tell us to use one of the tables to find the specific heat of the object. So when we look that one up from table 2.1, so they told us to use, the specific heat of the object is 0.3851. Now real quick, here's what you need to know. Actually, wait, one more thing. So we have a couple of other answers we can come up with just a very small amount of work, and that is simply that we can find our change in temperature for every one of these, okay? So when we calculate the change in temperature, which is T final minus T initial, we get negative 74.9 for our object. We get 0.9 for our water and 0.9 for our calorimeter. Now the only thing that's left is this box over here and then the box of what we're looking for. The thing I want you to know about any calorimetry problem is that if you get any row of this table with only one blank left, you can solve for it, okay? Q equals M times C times delta T. So for this energy here, I'm going to multiply negative 74.9 times 0.3851 times 345.1. And with significant figures, I get negative 9,950. And the author tells us that this negative sign simply means it's releasing energy. I'm going to do the same calculation here, 0.9 times 4.184 times 150. That gives us 600. Now, the other thing that you need to know, and that you should have read in the book, is that the change in energy of these two together will equal the opposite of the change in this one. So negative 9,950 equals this one plus this one, the opposite of that. So the opposite of 600 plus x. Okay, we'll talk about it in greater detail, but when I solve for that, I'm going to get 9,400. Okay, and that's simply negative 9,950 plus 600, which gives me 9,350, but I only have significant figures to hundreds, so I'm going to round it to 9,400. Now, I have every blank filled except this one. Q equals MC delta T. So then if I divide by M and delta T on both sides, I get that C equals Q divided by delta T times M. So that ends up being 9,400 divided by 4.5, which is my mass, times my delta T, which is 0.9. Okay? When I do that math, I'm going to get a final answer of 2,000. The answer is actually, with significant figures, that's what it is. The actual answer, 2320. It's actually 2,000. When you do this, you're going to get 2,320, but we have only one sig fig here, so we have to round it to 200. So our final answer here is 2,000. And that is how you solve a calorimetry problem. See you Tuesday.